Hello, in this video we're going to use implicit differentiation to solve related rates problems. For our warm-up, we're going to start by finding ds dt for s squared equals the square root of 1 minus 3t. Now if we wanted to, we could solve this equation for s first and then just take the derivative. If I tried to solve this for s, I would take the square root of both sides and I would get s equals plus or minus the square root of 1 minus 3t. That looks pretty complicated, and I'm not sure I want to take the derivative of that right-hand side. We could make it a little bit better by rewriting plus or minus the square root of the square root as just 1 minus 3t to the power 1/4. But here I still have to deal with the plus or minus, and I have to use the power rule combined with the chain rule. Let's try and find our derivative using implicit differentiation instead. So with implicit differentiation, we're going to take the derivative of each term in the equation with respect to the indicated variable, in this case t. To find the derivative of my first term, s squared, I'm going to take the derivative of s squared. The derivative of s squared is 2s, but that's the derivative with respect to the variable s, not with respect to the variable t. So here's where I need to use my chain rule for implicit differentiation to adjust for that change in variable. I take the derivative with respect to s and I multiply it by the derivative of s with respect to t. So the derivative of s squared with respect to t is 2s ds dt. And then I move on. Equals, now I want the derivative of the square root of 1 minus 3t with respect to t, and this is the proper variable. So here I don't have to do anything special. I just take my derivative using chain rule. This is in the form of the square root of stuff. So my derivative is 1 over 2 times the square root of the stuff times the derivative of the stuff. So the derivative of 1 minus 3t is negative 3. And now I want to find ds dt, so I'm going to divide both sides of my equation by 2s. So I get ds dt equals, now here I'm going to multiply the 1 and the negative 3, so I have negative 3 over 2 times the square root of 1 minus 3t, and now I'm dividing this by 2s, which is the same as multiplying by 1 over 2s. So I get negative 3 over 4 times s times the square root of 1 minus 3t. Number 2, find dv dt for 1 over v equals cosine squared of 3t plus 1. So again, we have a choice to make here. How much do we want to simplify before we start taking our derivative? I could just leave my equation the way it is and take the derivative implicitly. I would take the derivative of 1 over v, and then on the right I would use chain rule. This is actually a double chain rule problem to get the derivative of cosine squared of 3t plus 1. Another option I have is to simplify it a little bit first before I take the derivative. I can take the reciprocal of both sides. If I take the reciprocal of 1 over v, I get v. If I take the reciprocal of cosine squared of stuff, I get 1 over cosine squared of stuff, which is secant squared of stuff. So let's try it that way. We would have v equals secant squared of 3t plus 1. And then I can take the derivative in this form. So I'm not sure, I haven't tried it the other way. I'm not sure what's going to end up being easier. So we're just going to go with this. The derivative of v with respect to t, well, the derivative of v is 1 with respect to v, so it's 1 times dv dt equals, and anytime you have a trig function raised to a power, I recommend you rewrite it, moving the power to the outside so that it's easier to see how we're going to use the chain rule here. This outside function is in the form of stuff squared. So my derivative is going to be 2 times the stuff to the power 1 times the derivative of the stuff. So now I have to take the derivative of the secant of 3t plus 1. The derivative of secant stuff is secant stuff tangent stuff. So I have secant 3t plus 1 times tangent 3t plus 1, and then times the derivative of the stuff. So the derivative of 3t plus 1 is 3. So my final answer here, I'm going to multiply this 2 and this 3 together to get a 6 in front, and then I have secant times secant, and the arguments here match, so I can combine them as secant squared 3t plus 1 times tangent 3t plus 1. Number 3, find dr dt for t plus 1 squared times 1 minus 2t all over r equals 2. Now we could just go ahead and start taking the derivative as is, but there's a lot of stuff going on the left-hand side. We've got quotient rule in our outermost function. We've got product rule when we have to take the derivative of the top of this, and we've got chain rules involved in taking the derivative of the top as well. I think if we simplify this a little bit first before we even start to take our derivative, we'll have a bit of an easier time. So I'm going to multiply both sides of this equation by r, and that way I'm not going to have to use the quotient rule. So multiplying both sides by r leaves t plus 1 squared times 1 minus 2t equals 2r. If we wanted to, we could expand all of the terms on the left and then not have to do product rule, but product rule doesn't look like it's going to be too bad here. So let's just take our derivative as is. On the left, I do have to use product rule, so I've got my first factor, t plus 1 squared, and my second factor, 1 minus 2t. So product rule tells us to take the derivative of the first factor, so it's 2 times t plus 1 to the power 1 times the derivative of the inside, but the derivative of t plus 1 is just 1. So times 1, I'm not going to bother writing that. So that's derivative of the first. Now we have to multiply that by the second plus the first, t plus 1 squared, times the derivative of the second. And the derivative of 1 minus 2t is negative 2. Now we're taking the derivative with respect to t, and the variable here is a t, so we don't have to do anything special. But when we get to the right-hand side, and we want the derivative of 2r, r is the wrong variable. We're taking the derivative with respect to t. So I'm just going to go ahead and take the derivative of 2r. The derivative of 2r is 2 with respect to r. So then we have to multiply that by dr dt to make it a derivative with respect to t instead of a derivative with respect to r. Now on the right-hand side, I can factor out a 2. I can also factor out a t plus 1. So when I do that, my first term leaves me with 1 minus 2t. My second term leaves me with minus, if we think of that constant, moving that to the front, minus, and then one of the t plus 1's factor out, leaving me with a t plus 1. Now if I divide both sides of this equation by 2, the 2's drop out, and I have t plus 1 times 1 minus 2t minus t minus 1 equals dr dt. So the 1 minus 1 is 0, and negative 2t minus t is negative 3t. So I have dr dt equals negative 3t times t plus 1. Now let's look at our first activity. A spherical balloon is being inflated at a constant rate of 20 cubic inches per second. How fast is the radius of the balloon changing at the instant the balloon's diameter is 12 inches? Is the radius changing more rapidly when d is 12 or when d is 16? So first, we're going to recall that the volume of a sphere with radius r is given by the formula v equals 4/3 pi r cubed. That's the volume of a sphere. Both v and r are changing as time t changes. So the balloon is being inflated. As time moves forward, then the volume is getting larger and the radius is getting larger. So both of these variables are changing, and we want to know how the rate of change compares. So both v and r may be viewed as implicit functions of t because they're both affected by time t. They're both changing with respect to t. And then we're going to differentiate both sides of our volume equation with respect to time t. So we have this equation, v equals 4/3 pi r cubed. We want to take the derivative with respect to t. So on the left-hand side, we take the derivative of v with respect to t. Well, the derivative of v is 1 with respect to v, and then times dv dt. On the right-hand side, 4/3 times pi is a constant, so we can use our constant multiple rule. Our derivative is going to be 4/3 times pi times the derivative of r cubed. The derivative of r cubed is 3r squared with respect to r, but we want the derivative with respect to t, so now we have to multiply that by dr dt. So dv dt, that's the derivative of volume with respect to time. That tells us how quickly the volume is changing with respect to time. So by how much is the volume increasing per unit increase in time? And we have an equation on the right-hand side that tells us that, and it's written in terms of r and the rate of change of r. Part B, at this point in the problem, by differentiating, we have related the rates of change of v and r. So we have our rate for v, dv dt, written in terms of the rate of change of r, dr dt. Recall that we're given in the problem that the balloon is being inflated at a constant rate of 20 cubic inches per second. Is this rate the value of dr dt or dv dt? Well, we can use the units as a clue. Cubic inches per second. Cubic inches is measuring volume, and seconds is measuring time. So this is going to be our volume with respect to time. The 20 is dv dt. So now we know dv dt equals 20 cubic inches per second. Part C, from Part B, we know the value of dv dt at every value of t. Next, observe that when the diameter of the balloon is 12, we know the value of the radius. So at the moment when the diameter is 12, so when diameter equals 12, radius equals 6. In the equation, dv dt equals 4 pi r squared dr dt, substitute these values for the relevant quantities and solve for the remaining unknown quantity, which is dr dt. Okay, so in other words, we're going to replace dv dt with 20. We know that's equal to 20. On the right-hand side, we can multiply this 3 by this 1/3, and that's going to cancel out. And then we just have 4 times pi times r squared, but we know at this moment in time when the diameter is 12 that the radius is 6. So r squared is going to be 36 times dr dt. And we can solve for dr dt. Dr dt equals 20 divided by 4 times 36 times pi. And I can simplify that. 20 divided by 4 is 5. So we get 5 over 36 pi. So we found in the last part that dr dt at the moment in time when the diameter was 12, so when the diameter was 12, that dr dt was equal to 5 over 36 times pi. And now we want to know what is that rate when the diameter is 16? So dr dt when diameter is 16, now when the diameter is 16, that means that our radius is 8. So we can go back to our equation for dr dt. We had dv dt equals 4 times pi times r squared times dr dt. dv dt was 20 equals 4 pi, and since r is 8, now r squared is 64 dr dt. And then dividing both sides by 4 leaves a 5 here. So now we get dr dt equals 5 over 64 pi. And let's put units on this value. 5 over 64 pi, it's dr dt. And so my units will be the units of r, and r is measured in inches, per the units of t. T is measured in seconds. So my units are going to be inches per second. And here, inches per second. When is the radius changing more rapidly? Well, it has a higher rate of change when d equals 12. 5 over 36 pi is a larger value than 5 over 64 pi. For this next set of problems, we want to differentiate our equations with respect to time t. Our first equation is the surface area of a sphere. The surface area of a sphere is given by a equals 4 pi r squared. So we'll take the derivative of the left-hand side. The derivative of a with respect to time t is dA dt. On the right-hand side, the derivative of 4 pi r squared. Well, 4 pi is constant, so it's going to be 4 pi times the derivative of r squared. So 4 pi times the derivative of r squared. The derivative of r squared is 2r with respect to r times dr dt, so that it's with respect to t instead of r. What do each of these rates represent? Well, the dA dt is how quickly the surface area is changing with respect to time. The dr dt tells us how quickly the radius is changing with respect to time. So this equation, we know it's an equation because we have an equal sign. This equation is relating the rate dA dt with the rate dr dt. That's why this is called a related rates equation. It's got two different rates in it, and we're seeing how they're equal to each other. Number 2, the volume of a sphere is given by the equation v equals 4/3 pi r cubed. So we worked with this one in the last problem. We're going to take the derivative of both sides with respect to time t. The derivative of v with respect to t is dv dt. On the right-hand side, 4/3 times pi is constant, so our derivative is going to be 4/3 times pi times the derivative of r cubed. The derivative of r cubed is 3r squared with respect to r times dr dt, so that it's with respect to t. And here the two rates that are being related are the volume of the sphere with respect to time and the radius of the sphere with respect to time. Number 3, the volume of a cone is v equals 1/3 pi r squared h. The derivative of v is dv dt. On the right, 1/3 pi is constant. The derivative of r squared h. Now don't make the mistake of just taking the derivative of r squared and multiplying it by the derivative of h. That's not how derivative of products work. We have to use the product rule here. So r squared is my first factor and h is my second factor. And remember, we're taking the derivative with respect to t. So r is the wrong variable and h is also the wrong variable. We're going to have to use our chain rule to compensate for each of those derivatives. So let's start our product rule by taking the derivative of the first factor. The derivative of r squared is 2r with respect to r times dr dt to make it with respect to t. So our product rule tells us take the derivative of the first factor, multiply it by the second factor, plus then you just take the first factor, that's not a derivative, it's just the first factor, r squared, times the derivative of the second factor. So now we need the derivative of h. Well, the derivative of h is just 1 with respect to h, but we don't want the derivative with respect to h, we want it with respect to t. So then we multiply by dh dt. Okay, so that one was a bit more complicated. Here we're actually relating 3 different rates. We've got dv dt, that's how quickly the volume is changing with respect to time. We have dr dt, how quickly the radius of the base of our cone is changing with respect to time. And then dh dt, how quickly the height of the cone is changing with respect to time. Number 4, the volume of a cylinder is given by v equals pi r squared h. So the derivative of v with respect to time is dv dt equals pi times the derivative of r squared h. Well, again, we need the product rule here. R squared and h are 2 different factors, so we're going to use the product rule. The derivative of the first factor is 2r dr dt times the second factor plus the first factor times the derivative of the second factor. The derivative of h is dh dt. Again, we're relating 3 rates. We've got how quickly the volume is changing with respect to time, how quickly the radius of the cylinder is changing with respect to time, and how quickly the height of the cylinder is changing with respect to time. Number 5, we're looking at the Pythagorean theorem. A squared plus b squared equals c squared. So a and b would be legs of our triangle, c would be the hypotenuse. So in a problem like this, instead of volume expanding or contracting, we have the size of the triangle might be expanding or might be getting smaller. So in either case, if one part of the triangle is changing, all 3 parts of the triangle are going to be changing. So let's take the derivative with respect to time. The derivative of a squared would be 2 times a with respect to a times dA dt if we want it with respect to time. Plus, the derivative of b squared would be 2b dB dt equals the derivative of c squared is 2c dc dt. So we have the rate of change of our first leg with respect to time, the rate of change of our second leg with respect to time, and the rate of change of the hypotenuse with respect to time. And finally, we have the right triangle ratio cosine theta equals x over 15. We're going to take the derivative with respect to time. So the derivative of cosine theta is negative sine theta with respect to theta times d theta dt if we want it to be with respect to time t equals the derivative of x over 15. So we're going to think of that as 1 over 15 times x. And then it's just the constant 1 over 15 times the derivative of x. Well, the derivative of x is 1 with respect to x times dx dt if we need it to be with respect to time. So here the 2 rates that we're relating are how quickly the angle is changing with respect to time and how quickly the side x of our triangle, the adjacent side of our angle theta, is changing with respect to time. Let's say the radius of a snowball changes as the snow melts. The instantaneous rate of change in radius with respect to volume would be dv dr, dr dv, dr dt, or dv dt. We want the rate of change in radius, so the change in radius with respect to volume. So the change in volume, delta r over delta v. So that's going to be dr over dv. dr over dv is choice B. Gravel is poured into a conical pile. The rate at which gravel is added to the pile is, okay, so we have gravel being poured and it's making a pile in the shape of a cone. The more gravel that's being poured onto the pile, the larger our cone is going to become. It's going to get wider, So the radius is going to increase, and the height is going to increase, and the volume is going to increase. So all of these different things are changing. But when it says gravel is poured into a conical pile, the rate at which gravel is added, it's referring to volume. So it wants to know the change in volume over time. So we're looking for dV dt. dV dt. Now we're going to walk through a related rates problem from start to finish. For this problem, we're told that air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? So in a related rates problem, we compute the rate of change of one quantity in terms of the rate of change of another quantity. Like we saw in the previous examples, we're going to have two rates in our equation. So let's read this problem one more time. Air is leaking out of an inflated balloon in the shape of a sphere. So we have a sphere. Since air is leaking out, our sphere is getting smaller. If our sphere is getting smaller, several things are changing. The volume is changing, right? The volume's getting smaller. And the radius is also changing. The radius is getting smaller. The surface area is getting smaller as well. But here we're specifically asked to find what is the rate of change of the radius. So we want to find dr dt, the change in radius with respect to time. What is it that we know? Well, we're given the rate of 230 pi cubic centimeters per minute. That's describing the volume. So the other rate that we have in our problem is volume. So we need something that's going to relate volume in terms of time and radius in terms of time. In general, here are the steps that we're going to follow to solve a related rates problem. First, we're going to draw a picture and label all given information. That's really going to help us understand what's going on. Step 2, we're going to write down the rate that we're given and the one that we need to find. In a related rates problem, you're always going to be given at least one rate, and you're going to be asked to find at least one rate. Sometimes more. Usually it's just those two. One that you'll be given, one that you're trying to find. But sometimes we will have additional rates in our problem, and that's okay too. So we're going to write down all of the given rates and the rates that we need to find using proper notation. And when I say using proper notation, I'm referring to Leibniz notation. The Leibniz notation is really important here because it's going to remind us when we take our derivative which variable it's with respect to. Step 3, we're going to write an equation relating our variables from step 2. Do we need a volume equation? Do we need an area equation? Do we need Pythagorean theorem or a trig equation? Based on the variables that we have in our problem, we're going to come up with an equation that has those variables in it. Step 4, we're going to take the derivative of both sides. That's how we're going to get our rates into our problem. We're going to differentiate implicitly both sides of the equation with respect to time. And then finally, after we take our derivative, we're going to substitute all of our known values into the problem and solve for that rate that we're looking for. Now let's walk through this problem from start to finish. So again, air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? So step 1, we draw a picture. I want to draw a picture of a sphere. Okay, I know this is not actually the picture of a sphere, it's just the picture of a circle. But for a sphere problem, really we just need a cross section. So it's going to look like a circle. And that's fine. I'm going to label any parts of the diagram I can. Right now it's just radius. Radius is the only part of the defining part of this sphere that I have. Step 2, we're going to write down the rate that we're given and the one that we're trying to find using proper notation. So I've tried to color code this to help us figure out how we translate from the words in the problem into our equations. So looking at the parts in green, we have air leaking out of a balloon, and that tells me that the volume is getting smaller. And if the volume is getting smaller, then I know that my derivative has to be negative. It's a decreasing rate. The rate of change of my volume over time is going to be negative. So that word leaking is going to tell me to make my derivative of volume negative. The problem's not going to tell me that it's negative. I just have to infer that from the fact that air is leaking out. So it's leaking out at a rate of. And as soon as you see at a rate of, we know we're talking about a derivative. So at a rate of 230 pi cubic centimeters per minute. And the units here are a huge clue as to what rate it's describing, because nowhere here does it say volume, but it is describing volume. And our clue is that the units are cubic centimeters. Volume is measured in cubic centimeters. So I know it can't be the surface area that they're giving us. It's got to be the volume because those units are cubic centimeters. Per minute is the bottom part of our derivative. It's going to be with respect to time. Time is measured in minutes. So this rate that they're talking about has to be dV over dt. So here's my dV over dt. I know that it's negative. I know it's equal to 230 pi, and I know the units are cubic centimeters per minute. So that's the rate that I'm given. That's the one that I'm given. So in step 2, we're always going to write down what is the given rate, and then we're going to write down what is the rate I'm trying to find. So that's the part that I've highlighted in yellow. In the problem, it says, at the instant when the radius is 4 centimeters, what is the rate of change of the radius? What is the rate of change of the radius? So that's what they want us to find. The rate of change means derivative of the radius. So dr, and again, it's with respect to time, at the instant, when. So it's with respect to time. We want to find dr over dt. That translates into dr over dt. Now the radius is constantly changing. Air is leaking out of the balloon. We don't know if it's leaking out of a balloon at a constant rate. It could be leaking out slowly at first and then really quickly, the smaller the balloon gets. We don't know that. So our derivative dr over dt might change as r changes. So we have to indicate, okay, when in time are we going to find the derivative? We want the derivative at a specific moment in time. And that's the part that's highlighted here in purple. When the radius is 4 centimeters, find the rate of change of the radius. So when the radius is 4 centimeters, and that's this part of the notation down here. The vertical bar here in my notation means when or at. So I want dr dt when r equals 4. This is the one we're trying to find. So step 2, we write down the rate that we're given and the rate we're trying to find. And we want to do this using proper notation. Step 3, we have to write an equation that relates our variables. Well, which variables? You're going to look at the rate that you're given and identify the variable right here. That's a V for volume. You're going to look at the rate that you're trying to find and identify that variable on top. That's little r, or radius. So I need an equation that specifically relates these two variables. That's my goal. I need to write an equation that relates volume and radius. That equation's not going to be given to us in the problem necessarily. We just have to come up with it ourselves. So I think, okay, well, what equation do I know that has a volume and radius of a sphere in it? And it's the volume of a sphere formula. So the volume of a sphere equals 4/3 pi r cubed. This equation relates volume V and radius r. And those are the variables that I need for my rates, the one that's given and the one that I'm trying to find. So this is the equation that I'm going to use for my step 3. Step 4, we differentiate both sides of our equation with respect to time. So here's my equation that I wrote in step 3. I'm going to take the derivative using implicit differentiation, term by term from left to right. So I start by taking the derivative of V. The derivative of V is dV dt. 4/3 pi r cubed. 4/3 pi is a constant. So the derivative is going to be 4/3 pi times the derivative of r cubed. The derivative of r cubed is 3r squared times dr dt. So now I have a derivative equation that relates my two rates. I've got a dV dt and I've got a dr dt. Our final step then is going to be to substitute all of our known values into the equation and solve for that rate that we were looking for. We were trying to find dr dt at the moment in time when r was 4. So I substitute in 4 for the r. I let 4 equal r. And in the problem, I was given dv dt, so I'm going to substitute in negative 230 pi for the dv dt. I substitute in 4 for the r, and then I simply solve the equation for dr dt. We do want to pay attention to our units. So it's going to be the units for r over the units for t. R was measured in centimeters. That's the radius of our sphere that was measured in centimeters. And then t is time. That was measured in minutes. So the units on our answer, dr dt, would be centimeters per minute. That might have seemed like a lot for one problem, but if you break it down step by step, that process is always going to get us to the result we want in the end. So let's try another problem. Here we have a water tank in the shape of an inverted circular cone. So inverted cone just means the point is at the bottom. The base has a radius of 6 feet and a depth of 8 feet. The cone has a depth of 8 feet. Suppose that water is being pumped into the tank at a constant instantaneous rate of 4 cubic feet per minute. Find the instantaneous rate at which the water level is rising when the water in the tank is 3 feet deep. So let's go through our process step by step. The first thing we're going to do is draw a picture. Now I have a photograph here, but it might be a little bit easier if I just kind of strip this down to a cone. So here's my cone, and what do I want to label on my cone? Well, I have a radius for my cone here. This is the radius for my tank. Water is being pumped into the tank, so somewhere here I have a water line. And I have another cone inside of this tank. The water itself is in the shape of a cone. So I have another little r here for my water. I've got the height of the tank, which we can call h. And then the cone that's formed by just the water, I have a little h there as well. Now the radius of the tank and the height of the tank, those things are constant. They're not going to change. The tank itself, that shell, is not going to change. What is changing is the water. The height of the water is changing. The radius of the cone made up of by the water is changing. So I'm going to label my constants with their numeric values. Let's read through our problem one more time. The water tank has the shape of an inverted cone with a base of radius 6 feet. So I know this part here is 6. And a depth of 8 feet. So I know that this height here is 8. That's not going to change no matter how little or how much water is in the tank. So now I've got this other cone that has a little radius and a little height here, and that's what I'm going to label as R and H. Those values are changing. The more water in the tank, the larger the radius, the larger the height. So I can't label those with actual numbers. We're going to leave them written as R and H and move on to step 2. Step 2, we write down the rate that we're given and the one that we're trying to find. So let's go back to our problem. It says water is being pumped into the tank at a constant instantaneous rate of 4 cubic feet per minute. Cubic feet per minute is describing volume. So I know that rate that they're talking about, the 4, is describing the change in volume with respect to time. So that means dV dt equals 4 cubic feet per minute. And it tells us that that rate is constant. So it doesn't matter what time t we are at, the rate of change is just going to be 4. So that's the rate that we're given. Now we're asked to find the instantaneous rate at which the water level is rising when the water in the tank is 3 feet deep. So the water level, how quickly is that rising? That's referring to the h in our diagram. We are being asked to find dH dt, the rate of change of the height of the water with respect to time. And this does change as time changes. So we're going to be finding it at this instant in time when the water in the tank is 3 feet deep. So when h is equal to 3. We have our rate that we're given and the one that we're trying to find. So step 3 now is to write an equation that relates our variables. Our variables are the v from the dv dt and the h from the dH dt. So I need an equation. I need to write an equation that relates v and h, the volume of a cone and the height of a cone. What equation do we know that has a v and an h in it in terms of a cone? Well, we can go to the equation for the volume of a cone. The volume of a cone, v, equals 1/3 pi r squared times h. So we have our equation that has a v in it and an h in it. The problem is we also have an r in this equation, and we don't have a rate for r. We're not asked to find dr dt, and we are not given dr dt. So I really don't want that r in my equation. If I leave the r in there, when I go to take my derivative in step 4, I'm going to have to take the derivative of this r variable, and that means since we're taking the derivative with respect to t, I'm going to have a dr dt in my equation. But I don't have any information about dr dt, so I don't want that. I want to try and avoid that. I also want to avoid having to do product rule here when I take my derivative. So if I could get that r out of the equation, that would really be helpful. So I'd rather just have my right-hand side in terms of h. Can we come up with an equation that relates r and h so that I can substitute the r out of the equation? Well, let's look at our diagram again. We have kind of this cross-section of a cone. If we look at just half the cone, we've got some right triangles here. This is a right triangle here, and it's sitting inside of this larger right triangle here. So we have similar triangles, similar right triangles. We can come up with a proportion. So when you have similar triangles, the corresponding parts are going to be similar. So my little leg to my big leg, if I look at that ratio, the little leg to the big leg in my smaller triangle is going to equal the little leg to the big leg in my larger triangle, because these are similar triangles. I have this proportion now. I've got small leg to long leg equals small leg to long leg. I want to solve this for r. So I'm going to multiply both sides of the equation by 8, and I'm going to multiply both sides of the equation by h. I get 8r equals 6h. I'm trying to solve for r, so now I divide both sides by 8. I get 6h over 8, which reduces to 3h over 4. R equals 3h over 4. That's awesome, because now I have something I can substitute in for r. I know that r equals 3h over 4. So now my volume equation becomes 1/3 pi times 3h over 4 squared times h. Now I have an equation that only has my two variables v and h. That's exactly what I want, an equation that only has those two variables, v and h. I'm not going to take the derivative yet, though. I want to simplify first, because right now I've got an h squared term and times another h, and I don't want to have to do product rule. It makes more sense to simplify this first. So v equals, I've got 1/3 pi. 3h squared is 9h squared over 4 squared is 16, and times h again. So this is, okay, let's do this. 9 divided by 3 is just 3 now. So I have 3 pi over 16 times h cubed. Now when I go to take my derivative, I'm just going to have to use power rule and, of course, implicit differentiation. So we're ready for the next step. Step 4, we're going to take our derivative of both sides with respect to time t. The derivative of v with respect to time t is dv dt. equals 3 pi over 16 times h cubed. The 3 pi over 16 is constant. So I've got 3 pi over 16 times the derivative of h cubed. The derivative of h cubed is 3h squared with respect to h times dh dt. That's our implicit differentiation there. Looking good. And now we're ready to move on to our last step. Step 5 is where we substitute all of our known information in to our derivative equation and solve for the rate that we're looking for, the dh dt. So we want to substitute in for all the variables except for the dh dt. Well, what does dv dt equal? dv dt equals 4. So I'm going to substitute 4 in for the dv dt. Equals 3 pi over 16 times 3 times h squared. What is h? What is h? Well, remember, we're trying to find the derivative, dh dt, when h is 3. So the value of h at this moment in time is 3. So I'm going to put in 3 squared times dh dt. And now we get dh dt equals, so we have on the right, we've got 3 times 3 is 9, times 3 squared, that's another 9. 9 times 9 is 81. So 81 pi over 16. I'm going to divide both sides by 81 pi over 16. Dividing by 81 pi over 16 is the same as multiplying by 16 over 81 pi. So I have 4 times 16 over 81 pi. That's 64 over 81 pi. And let's just get a decimal approximation for that. And I'm getting 0.252. Then our units for dh over dt will be units of h per units of t. H, the height, is measured in feet. Per t, the time, is measured in minutes. So my units are going to be feet per minute. 0.252 feet per minute. Our next example, a television camera is positioned 400 feet from the base of a rocket launching pad. The angle of elevation of the camera has to change at the correct rate in order to keep the rocket in sight. In addition, the autofocus of the camera has to take into account the increasing distance between the camera and the rocket. We assume that the rocket rises vertically. Suppose the rocket's speed is 600 feet per second. At the instant, it has risen 3,000 feet. How fast is the distance from the television camera to the rocket changing at that moment? So let's just focus on part A. Step 1 is to draw a picture and label the relevant information. So I have my camera down here, and the rocket is rising vertically. We're told that the camera is 4,000 feet from the base of the launching pad. So I'm going to make a right triangle here. And I know that this is 4,000 feet. That's constant. That's not changing. The horizontal distance from the camera to the rocket launching pad is 4,000 feet. And then we've got the rest of our right triangle right here. The angle of elevation from the camera has to change at the correct rate. So angle of elevation, that's our theta right here. And the autofocus has to take into account the increasing distance between the camera and the rocket. So the distance between the camera and the rocket is going to be the hypotenuse of this triangle. So that's what I'm going to call, let's call it Z. Suppose the rocket's speed is 600 feet per second. At the instant, it has risen 3,000 feet. So I need a variable over here for how far it has risen. I'm going to call that y because it's a vertical change in position. And normally I would call that horizontal leg x, but we know that's constant. That's 4,000 feet. So I think I've labeled all the parts I need to label on my picture. I'm going to move on to step 2. In step 2, we write down what is the rate that we're given and what is the rate that we're trying to find. So we are told that the rocket's speed, that's the rate of change, that's the derivative of the change in position, the change in y with respect to time t. So our dy dt, that's the speed of the rocket. And we're told the speed of the rocket is 600 feet per second. At the instant it has risen 3,000 feet. So dy dt when y is 3,000 equals 600 feet per second. And usually in these problems, it's not going to point out whether this should be positive or negative, so you have to stop and think about that. Look at your picture. As time increases, y is increasing, and that tells me that my derivative needs to be positive. So positive 600 feet per second. That's the rate that I'm given. Now, what is the rate that we're asked to find? We want to find how fast the distance from the camera to the rocket is changing at that same moment. So the variable I chose to represent the distance between the camera and the rocket is z. I want to find dz dt at that same instant, so when y equals 3,000. Now step 3, we need to write an equation that relates our variables, the y from our dy dt and the z from our dz dt. I need to come up with an equation that involves y and z. So let's go back to our picture. We need an equation with a y in it and a z in it, and I can also include my constant value. Anytime you can include constants, that's nice. So I see that since I have a right triangle and I want something that involves all three sides of this right triangle, I'm going to use Pythagorean theorem. I know that leg squared plus leg squared equals hypotenuse squared. So I've got z squared equals 4,000 squared, it's going to be a large number, 4,000 squared plus y squared. Okay, there's my step 3. Now step 4, we take the derivative of our equation with respect to time t. The derivative of z squared is 2z dz dt equals the derivative of 4,000 squared is 0. The derivative of a constant is 0. So that's convenient. The derivative of y squared is 2y dy dt. Now I can divide both sides of my equation by 2, simplify it a little bit. And now we're ready for step 5, where we substitute in all of our known values. Do we know the value of z? Well, we're looking for dz dt at the instant when y is 3,000. So I know the value of y is 3,000. And I know dy dt is 600. That was given. So the right-hand side here is going to be easy. Y is 3,000 and dy dt is 600. But I'm trying to solve for dz dt. I still have this extra z over here. I need to put something in for z. So we need to figure out at this moment in time, when y is 3,000, what is the value of z? Let's go back to our picture. So when y is 3,000, so I'm going to write at y equals 3,000. Can we find the value of z? Yes, we can, because at this moment in time, I know the measure of both legs of this triangle. So I can use Pythagorean theorem to find out z when y is 3,000. I know y is 3,000 and the other leg is 4,000. So at y equals 3,000, I'm going to put another at here just to remind myself that this is not a constant value. This is just at this particular moment in time. My z, well, I can say z squared is going to equal 3,000 squared plus 4,000 squared. So z is going to be the square root of 3,000 squared plus 4,000 squared. Let's find that on our calculator. We get z equals 5,000. So at this moment in time, y is 3,000 and z is 5,000. Now it's really important that I did not do this before I took my derivative, that I didn't, in my picture, that I didn't say the hypotenuse is just 5,000. The hypotenuse is changing with respect to time. That is a variable. But after we take the derivative, we can find the value at a specific moment in time. So that's why I made it a different color in pink, and I wrote my little @ symbol to remind myself that that's not always the value of z. It's only the value of z at this one moment in time. Okay, so now we can solve for dz dt. dz dt equals 3,000 times 600 divided by 5,000. Okay, so we can divide top and bottom by 1,000 right away, and then we get 1,800 over 5, which is 360. Now the units here for dz dt will be units of z per units of t. Z is measured in feet and t is measured in seconds, so my units are going to be feet per second. dz dt is measured in feet per second. So 360 feet per second is how fast that distance is changing at this particular moment in time. Now part B, if the camera is following the rocket, how fast is the camera's angle of elevation changing at the same moment? So some of this problem we already have done, and we can use the work that we've done. Step 1, draw our picture, label our values. We've done that. Step 2, write down the rates that we know and the one that we're trying to find. I erased it, but we can still use our work from last time because it says how fast is the camera's angle of elevation changing at that same moment. So we know at this moment, we know dy dt. We have dy dt at this moment, at the moment when y equals 3,000. We know that that's equal to 600 feet per second. That was given in the problem. But we also know the rate that we found, that how fast is that distance changing. We know at that same moment in time, dz dt when y equals 3,000 is 360 feet per second. So we can use that rate as well if we need to. What is the rate we're trying to find now? It's asking us how fast, so that means the rate, how fast is the camera's angle of elevation changing? The angle of elevation is the theta that I labeled in my diagram. So now we want to find d theta dt at that same moment in time. So when y equals 3,000. And we also know that when y equals 3,000, z equals 5,000. So we can use that if we need to as well. So we've done steps 1 and 2. Now step 3, we need an equation that relates our variables. So we're going to use the rates that we know and the one we need to find to come up with an equation. So we can use y, z, and theta. Y, z, and theta. Let's go back to our picture. What equation do we know that we can write that involves y and z and theta? Well, we do have a right triangle, so we can use a trig equation. Y is the side opposite of theta. Z is the hypotenuse. Opposite over hypotenuse is the sine of theta. So we could write an equation sine theta equals y over z, and that would have our 3 variables in it. But there's actually an easier one we can use. If we can avoid using one of our variables, that just makes everything simpler. That's one less variable that we have to take the derivative of implicitly. And we have a constant leg in our triangle of 4,000 feet. So let's use that one. Let's take advantage of that. If I write an equation with theta and 4,000 in it, then I only need one other side, the z or the y. It doesn't matter which one. I'm just going to stick with the y. So an equation that relates theta and 4,000 and y, that's theta, the opposite leg, and the adjacent leg, would be a tangent equation. I can say tangent of theta equals y over 4,000. And now I'm going to go on to my next step and take the derivative of both sides of this equation implicitly. So the derivative of tan theta is secant squared theta. That's the derivative with respect to theta. We want the derivative with respect to time. So we have to multiply by d theta dt equals the derivative of y over 4,000. You can use quotient rule if you like, but it's a lot simpler just to think of this as 1 over 4,000 times y. Then our derivative is 1 over 4,000 times the derivative of y. The derivative of y is 1 with respect to y times dy dt. And there's our equation. So now we're going to move on to step 5, where we're substituting in all of our known values. The dy dt we know is 600. So on the right-hand side, I've got 1 over 4,000 times 600, or 600 over 4,000. The d theta dt is what I'm trying to find. And then I have to multiply that by secant squared theta. Well, what is secant squared theta? Let's go back to our picture. Secant theta, in terms of our right triangle, is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent, z over 4,000. And at this moment in time, when y is 3,000, I know z is 5,000. So at this moment in time, secant of theta is 5,000 over 4,000, or 5 over 4. I need the secant of theta squared. So it's going to be 5 over 4 squared. 5 over 4 squared is 25 over 16. So now I'm going to divide both sides of my equation by 25 over 16. Dividing by 25 over 16 is the same as multiplying by 16 over 25. So I have 600 over 4,000 times 16 over 25. And going to my calculator, that is 0.096. So now we just need to figure out our units. This is d theta dt, so we have units for theta per units for t. The theta is my angle, and we're always going to use radians here, not degrees, because when we take the derivative of theta, our derivative rules that we've learned for sine theta, cosine theta, tangent theta, and so on, all of those derivative rules are assuming that our theta is measured in radians. And since we did take the derivative of tan theta, we're assuming that our theta is in radians. Now the time t is measured in seconds. So my units are going to be radians per second. 0.096 radians per second. If you do want to convert that to degrees, if that makes it more meaningful, we can simply multiply our radians per second by 180 and then divide by pi. So if I multiply by 180 and divide by pi, I get approximately 5.500 degrees per second. Okay, so you can see from all these examples, it's that same 5-step process. Draw and label your picture, write down the rate that you're given and the one you're trying to find, then write an equation that uses the variables in those rates, take the derivative implicitly with respect to t, and then substitute in all of your known values after you find the derivative.